Okay, more conversation from Chapter 6. We're going from balancing equations to determining how all of these things are accounted for by masses in a realistic way by what we call stoichiometry. So let's take an example of a reaction. This one is called ethylene, this funny compound of 2 carbons and 4 hydrogens. Reacts with something we call hydrogen chloride, yes, HCl gas, and it makes something that's known as ethyl chloride, used as a topical anesthetic in various ways. You could draw the structures of all those compounds, but that's not the point right now. And what would we have to do if we wanted to know how much ethylene and how much hydrogen chloride are needed to make a useful amount of the ethyl chloride? Maybe manufacturer needs to know how much it takes and how much it's going to cost them. So in order to do that, we have to be able to relate the atoms and molecules to things that we're going to see on a macroscopic level, namely grams. And so to do that, we're going to calculate molecular weights, where for a molecule, we'll add up the sum of all the atomic weights of all the atoms in a molecule from our good old friend, the periodic table. Or a formula weight is another way of saying it in a more generic way, because it's not just for molecules. It will apply to any formula unit of a compound, whether molecular or ionic. Now, these examples here are shown are molecular because they're combinations of nonmetals. Not hard, but let's look at how these are done. So if it's going to be the ethylene with 2 carbons and 4 hydrogens, you simply add up the molar or the atomic weights as shown on the periodic table. And carbon is going to be 12 to 3 sig figs. That's totally fine. And 2 of those plus 4 times hydrogen to 2 sig figs, it's 1. And so we can add that up and we get 28 AMU is the molecular weight, formula weight for ethylene. HCl, similarly, 1 AMU is for hydrogen, and the 35.5 AMU is for chlorine. Add them up and you get 36.5 AMU for the molecular weight for HCl. But now we have to think in terms of something besides atoms. We think in terms of moles of atoms and molecules. So we'll use the molar mass. We've learned about this previously. We're bringing it back now. The molar mass is the sum of the atomic weights of all the atoms in a molecule or an ionic formula unit. But the mass of the mole is the formula weight expressed in grams. So if ethylene C2H4 had a formula weight of 28 grams, which we saw on the previous slide, the mass of 1 mole of ethylene is 28.0. So this is commonly going to be expressed as 28.0 grams per mole, as a reminder that that's per an entire mole. Same thing is true for HCl. The atomic weights added up to 36.5. And so if you take a whole mole of them, 6.022 times 10 to the 23rd of them, you're going to get 36.5 grams for each mole of HCl. The product of the reaction we were looking at is going to be a sum of the two, because the two combine to make the product that we were looking at. So you're going to have 1 mole is going to be 2 times the mass of carbon, which is 12, and 5 times the mass of hydrogen, which is 1, plus 1 times the mass of chlorine, which is still not a hard number. It is going to be 35.45, or let's just call it 35.5. And you add those up, and guess what you get? Should be the sum of all of that should come out to be 24 plus 5 plus 35.5 is going to be 64.5. And if you added those other two numbers together, surprise, surprise, you should actually get that, because one of each should combine to make this number of grams for 1 mole of the product, the ethyl chloride. So let's see how this kind of reaction might work out. We have a balanced equation here where the ethylene is reacting with HCl. So if you had 1 mole of C2H4, we just said that its mass is 28 grams, and 1 mole of HCl, whose mass was 36.5 grams, you should make 1 mole of the product, C2H5Cl ethyl chloride, ethyl chloride, and the mass of that is going to be 64.5 grams. In other words, 1-to-1 correspondence of the reactants should give you 1 mole of the product, and their masses should add up. Now, not all the examples are as simple as this, and so we'll have to work in detail to figure out how to calculate things. So if you don't have exactly 1 mole of your reactant, what do we have to do? So we'll have to say, what if we start with 15 grams instead? 15 grams just is a number to try. And so if you have 15 grams of your ethylene, you'll use your molar mass and make sure you set it up so that things make sense. Molar mass is always grams per mole. And set it up in the fashion so that the units will cancel. Grams go on the bottom to make sure it cancels. And when you set it up this way, the answer is in moles, and we get a fraction of a mole. 15 grams is surely a fraction of 28 grams in that sample of the ethylene. So we can do the same thing then to decide how it's going to react with the HCl in a similar fashion. So if you have 0.536 moles of the ethylene, what would you have to have of the HCl? So if we have them reacting in a 1-to-1 proportion of molecules, the moles will react in 1-to-1 proportion as well. And so you need 0.536 moles of the HCl. Again, we'll set this up in a fashion that the units are going to cancel, but we're using the molar mass here. The molar mass being 36.5 grams of HCl per mole of HCl. If the units are set up properly, the answer you end up with now is grams. So it takes 19.6 grams of HCl for the 15 grams of the ethylene in our reaction. So the next question is, if we were going to predict then from this how much of the product will you get, well, then we should be getting the same number of moles of the ethyl chloride. So it should be 0.536 moles of C2H5Cl. And how much is it going to weigh? How much is it going to come out to be? Well, we have to figure out in terms of using the molar mass again. And the mass for 1 mole of this compound, as you recall, was 64.5 grams for the previous slide. If you set it up carefully, and please be very cautious to write them out, it's much, much wiser, we can determine exactly how many grams are expected. If you put it into your calculator and do the math, you should get something to the effect that 34.5, or let's round it up, 6 grams of C2H5Cl is expected. But this should make sense because we're combining all of 15 grams of the ethylene plus all of the 19.6 grams of the HCl to make our product. And so we verified it in 2 different fashions that's how you're going to come up with these things. Now, this is a very simplistic example, and we'll find others that are more complex as we go. Part of the reason this reaction is very simplistic is that it takes a 1-to-1 proportion of each reactant to make 1 mole of product. What about the ones, and how will we deal with ones when they're not? We are going to look at the balanced equation and do what we call a ratio of moles, mole ratios of compounds reacting in a process. So here's another reaction. Hydrogen reacting with nitrogen to make ammonia. So 3 moles of hydrogen react with 1 mole of nitrogen to get 2 moles of ammonia. And we can use all kinds of ratios of these reactants and products in our calculations. So if you're looking at the ratio of hydrogen to nitrogen, it would be 3-to-1. If you're looking at nitrogen to hydrogen, it would be 1-to-3. If you're looking at hydrogen to ammonia, it's 3-to-2. Or ammonia to hydrogen, it's the reverse, 2-to-3. Nitrogen to ammonia is 1-to-2. And ammonia to nitrogen is 2-to-1. So any of those possible mole ratios could be used in our calculations, which wasn't necessary in the previous example because the coefficients were all 1 because 1 of each combined to make the product. So what we do is we call these things mole ratios, and we're going to use these all the time in doing our calculations in stoichiometry. So you've got to be very careful that you set them up and write them with units, because if you don't write the units in, we'll forget what was supposed to cancel. So a ratio of moles is called a mole ratio, but it's going to be moles of any reactant with any product or combinations of these things. So let's look at another example. In this picture, we see a Bunsen burner heating up something in a test tube. That is an interesting reaction. So we're going to see what it is. There's a compound in there that's going to generate oxygen gas when it's heated, and then we'll have to figure out what the balanced equation for the process is. So we're heating it up and making oxygen gas. Well, it turns out that compound in there is KClO3. Now, if you can remember your polyatomic ions, here's a good place to use one. KClO3. Potassium, well, which one is it? It should be the chlorate, right? Chlorate corresponds to ClO3. And we're writing, to begin with, an unbalanced equation because we have to start with formulas being correct. Remembering that potassium is a +1 cation, chlorate, and its various other chlorine, oxygen ions. Anions are all anions of -1 charge. Potassium is +1, chloride is -1, so that formula is correct. And oxygen is always O2 because it is, in fact, a diatomic element, right? Okay, so what are we going to have to do to balance this equation? Before we go any further, we'll just have to get the math right and add them up. So 1 potassium on the left, 1 chlorine on the right. So far, so good, one of each. But oxygen's not coming out even. If you've got an odd number on one side and an even number on the other side, we always have to do something to make them come out right. So 3 on the right and 2 on the left will get us 6 oxygens on each side. But now we have to change the number of potassiums and chlorine in the reaction, and putting a 2 in front of potassium chloride gets that job done there. So now we have a balanced equation for the process with 2 potassium, 2 chlorine, and 6 oxygen, both on the left and on the right. All right, now let's make an example, and let's presume that we might have 5 moles of potassium chlorate, just a simple number, heated up. How many moles of oxygen are going to be produced? So this is simply a ratio of moles. Nobody said anything about grams yet, so don't worry about them. And so what are we going to have to do? So we'll look at this in terms of ratios of moles. So if you start with 5 moles of KClO3 potassium chlorate, and we're looking at oxygen as the product in proportion to it, how many moles are going to be produced, we'll look at the coefficients in the balanced equation. So the 2 on the potassium chlorate and the 3 on the oxygen is what tells us the proportion in which they react. And so the way to do this to make sure that ratio allows something to cancel is you put the one on the bottom that needs to cancel out, so the potassium chlorate belongs on the bottom with its coefficient from the balanced equation. And then the oxygen goes on the top, so 3 moles of oxygen goes on the top. Remember that the balanced equation can refer to atoms and molecules, but also moles. And so we'll use this mole ratio to relate these 2 species in the reaction process. Now, setting this up correctly means that the moles of potassium chlorate should cancel. And now it becomes a simple math problem. If you don't even have a calculator, you can probably get there and tell me that 15 divided by 2 might not be the hardest thing. It would be 7.5 moles of oxygen. If you want to know how much this weighs, well, then that requires more steps of stoichiometry, which we will be coming to one piece at a time. And so don't forget, whenever we do these stoichiometry problems, chemists are going to do it with moles, haha. And don't forget Avogadro's number, 6.02 times 10 to the 23rd. And once you've seen 6.02 times 10 to the 23rd atoms, you've seen a mole. And mole problems are always solved with Avogadro. This will be enough for this part of our stoichiometry discussion. The next part will be on part 2, where we will come into complete calculations, including grams. Please ask questions if you need more help. See you in class.